Our goal is to calculate the molar solubility of lead 2 chloride, which is a slightly soluble compound, and we're given the solubility product constant, Ksp, which is equal to 1.6 times 10 to the negative 5 at 25 degrees. This time, though, we're starting out with a 0.1 molar solution of potassium chloride. So if we have a beaker here and we have a 0.1 molar solution of potassium chloride, that means the concentration of potassium ions in solution is 0.1 molar, and the concentration of chloride anions in solution is also 0.1 molar. So we have some solid lead 2 chloride, right? So this is supposed to represent our solid lead 2 chloride. And what our problem wants us to do is to figure out how much of our lead 2 chloride will dissolve if we add it to our solution of potassium chloride. So some of the lead 2 chloride is going to dissolve and eventually reach equilibrium. So let's go ahead and write that out here. We have solid lead 2 chloride, and some of it's going to dissolve and give us lead 2 plus ions in solution. And we would also get chloride anions in solution, so we would get Cl minus. When you balance this, you need a 2 in front of our chloride anions, and everything else would get a 1. So we first think about the initial concentration of our products. So what's the initial concentration of Pb2+? So before we've added our lead 2 chloride, right, nothing has dissolved yet. So we don't have anything for our concentration of lead 2+, right? So nothing's dissolved. Before the lead 2 chloride has dissolved, we don't have anything for the concentration of chloride anions from lead 2 chloride, but we do have a concentration of chloride anions from our 0.1 molar solution of KCl. So we're starting with an initial concentration of 0.1 molar for our chloride anions. Next, we think about the change. So some of our lead 2 chloride is going to dissolve, and let's make that concentration X. So we're going to lose a concentration of lead 2 chloride. And for every 1 mole of lead 2 chloride that dissolves, we get 1 mole of lead 2 plus ions in solution. So if we lose X for lead 2 chloride, we gain X for lead 2 plus. And for every 1 mole of lead 2 chloride that dissolves, we get 2 moles of chloride anions. So we're going to gain 2x here for our chloride anions. So our common ion for this problem is the chloride anion because we have 2 sources, right? One source was from our potassium chloride, and one source was from our lead 2 chloride. So at equilibrium, right, our concentration of our products would be 0 plus X for lead 2 plus, or X, and 0.1 plus 2X for chloride anions. So this is equal to 0.1 plus 2X. Next, we write our equilibrium expression, right? So our solubility product constant Ksp is equal to concentration of our product, so concentration of Pb2 plus raised to the power of the coefficient. So our coefficient here is 1, so this is to the first power. And we multiply that by the concentration of chloride anions in solution, Cl minus, and we raise that to the power of the coefficient. Our coefficient is a 2, so we raise that to the second power. Next, we can go ahead and plug in our solubility product constant. So Ksp is equal to 1.6 times 10 to the negative 5. So 1.6 times 10 to the negative 5 is equal to the concentration of lead 2 plus ions at equilibrium, which we already figured out was X. So this is X to the first power, times the concentration of chloride anions at equilibrium, which is 0.1 plus 2x squared. So we have 0.1 plus 2x squared. So next we have to solve for x. Right? So on the left side we have 1.6 times 10 to the negative 5 is equal to x to the first. And over here, 0.1 plus 2x, we could do that math, but to make our lives easier, we usually make the assumption that x is really small compared to 0.1. And if x is really small compared to 0.1, 0.1 plus 2x is approximately the same as 0.1. So let's go ahead and put in 0.1. So we have 0.1 instead of 0.1 plus 2x. And 0.1 squared is 0.01. So on the right side we have x times 0.01, and this is equal to 1.6 times 10 to the negative 5. So when you solve for x, x is equal to 0.0016 molar. And so this would be the concentration of lead 2 plus ions in solution, right? If we go back up here, we can see that the concentration of lead 2 plus ions is X. So that's our concentration. And that's also the molar solubility of lead 2 chloride, right? That's how much dissolved. So let's go ahead and write that in here. So our goal was to calculate the molar solubility, and it was equal to 0.0016 molar. Now keep in mind, this is the molar solubility for lead 2 chloride in our solution of potassium chloride. Right? So this is in potassium chloride. In the video on solubility product constant, we found the molar solubility when it was just pure water. And if you look at that video, we calculated the molar solubility to be 0.016 molar. So this was in pure water. So we didn't have any potassium chloride here. And notice what the addition of the potassium chloride did to the molar solubility, right? It decreased the solubility by a factor of 10, right? If you compare these values here, so the solubility in pure water was 0.016, and now the solubility has decreased. It's 0.0016, right? So 1/10 the original solubility. And this is due to the presence of a common ion. Right, and our common ion was the chloride anion. So according to Le Chatelier's principle, right, a system that's disturbed from equilibrium will shift its equilibrium position to relieve the applied stress. So we can use that idea in this situation. So if we think about our reaction being at equilibrium, right, and you increase the concentration of your product here, if you increase the concentration of your chloride anions, right, that's our stress. Our stress is increased concentration of a product. The equilibrium shifts to decrease the stress. So the equilibrium shifts to the left, and the excess chloride ions that we have combine with lead 2 plus ions to form more of our solid. Therefore, we've decreased the solubility of lead 2 chloride due to the presence of our common ion. Notice that KSP doesn't change, right? KSP is still 1.6 times 10 to the negative 5, but the molar solubility has been affected by the presence of our common ion. So a common ion decreases the solubility of our slightly soluble compound, in this case by a factor of 10. So we can use this concept in a laboratory separation. So let's say we had some solid lead 2 chloride, and our goal was to isolate all of the solids. Right? So before we filtered it, we could add a common ion. We could add a source of chloride anions, right? And due to the common ion effect, that decreases the solubility of lead 2 chloride, which means we're going to get more of our solid, because our goal is to isolate as much of our solid as possible. So that's one use for the common ion effect in a laboratory separation.